The real world is full of uncertain outcomes. It is up to us as business analysts to model these uncertain outcomes and to advocate for good decisions in the face of this uncertainty. We will decide where to locate a new store even though its prospects are uncertain. We will decide how many laptops to keep in inventory despite not knowing how many we can sell. We will decide the price for airline tickets despite not knowing the effect it might have on demand. We make all of these decisions through modeling the real world using math and computing power. Before we jump into more complex scenarios, let's learn how to model some simple real-world uncertainty. The roll of a die. Here is a 6-sided die. Let's toss it. Now, how do we model the outcome of this toss in the math world? One way, a nice intuitive way, is to use a probability table. The table associates each possible outcome with the probability of occurrence. In this case, each of the 6 sides have equal probability of occurring, and that probability is 1/6. Easy peasy. Now we toss the die again, and while the outcome is fixed, it is still uncertain to us as the die rolled off the screen. The cool thing is that the previous probability table still describes our uncertainty. We can use probability to represent both our lack of knowledge as well as the inherent randomness in the world. In both cases, the tossed die spinning in the air and the off-screen die with unknown outcome, we will use the math world language of random variables to model our uncertainty. We use capital letters to represent random variables. Read the 3 horizontal lines here as defined as, and thus uppercase or big X is defined as the unknown outcome of a single die roll. I find it helpful to always be explicit about defining this nice mapping between math world letter X and real world narrative. The math world letter will allow us to be more concise when talking about this real world phenomenon. Back to the real world, we now toss the die and observe its outcome, a 6. In the math world, we use a lowercase letter to represent a realization or observation of the random variable. In this case, lowercase x is an observation of uppercase X, and we say lowercase x equals 6, or just x equals 6, and you know it's the lowercase one. Mathematically speaking, a random variable is not truly the mapping of outcomes to probabilities, it is only the mapping of outcomes to real numbers. We go slightly further with random variables. We assign a probability distribution to the random variable, which allocates plausibility across all potential outcomes. For our purposes, when we use the term random variable, we will usually mean this double mapping of outcomes to real numbers and real numbers to plausibility measures. When there is a countable number of outcomes, our last column represents a probability that big X equals little x. More generally, our plausibility measure, which is not always a probability, will be denoted little f of x. This notation allows for the cases where infinite outcomes are possible, not just 1 through 6, and hence little f of x is not directly interpretable as a probability. Mathematicians often prefer to be concise and terse as opposed to expressive and easily comprehensible. The compactness of the math world is both a strength and a weakness. We will learn to decipher the terse notation and make it part of our own language. Here, instead of assigning a probability distribution using a large table of outcomes and associated probabilities, we get mathy and simply say that random variable x is distributed as, that is how to read the tilde, x is distributed as a discrete uniform random variable with 2 parameters, 1 and 6. With a distribution name, discrete uniform, and parameters specified, 1 and 6, you actually know everything there is to know about the random variable. In this case, that means everything that the probability distribution table had told us, all possible values and their associated plausibility. Wikipedia becomes a great resource when encountering name probability distributions. Just type the distribution name and read about it. Some of the info will be too technical, but there is always some good stuff on the right side here. Specifically, the parameters and the support are nice things to know. As we go back to our discussion of discrete uniform, let's just expose you to some math notation. As a business analyst, you will need to gain some fluency, not only in the real-world decisions you are modeling, but also in the math world concepts and notation that you will leverage for insight. In this case, we say the support of the probability density function, f of z, where the big Z subscript tells us which random variable's probability mass or density function to use, in this case big Z's probability mass function, and the little z in parentheses says this function takes a realization value, little z, as input. Thus the support of f of z is all possible values of little z that are part of the real numbers, such that, read the colon as such that, the plausibility measure is greater than 0, meaning there is at least an infinitesimally small chance of the realization, little z, occurring. That is a mouthful, so let's ensure we also gain some intuition for this tough notation. For the discrete uniform, the notation implies that it is plausible to see integer outcomes from integer a to integer b. Little f of z, in this case known as the probability mass function, means each possible value has equal probability of occurring, and the probability is 1 over the number of possible outcomes. With only 6 possible outcomes, all this math notation is not that useful. But now let's say we want to model this real-world bingo example.
Welcome to Movie Trailer Voice Bingo. Ready to play?
In bingo, there are 75 possible integers that get picked with equal probability, starting from 1 and going to 75. I do not want to make a 75-row table to describe my uncertainty in what bingo ball gets selected.
Clickety-click, 66.
For example, what the probability of drawing ball number 66 is. So instead we use our nice terse math notation, let x be the outcome of the first bingo ball drawn, and therefore we model our uncertainty in x. And we say x is distributed, discrete uniform with parameters a equal to 1 and b equal to 75. This is much easier to write than the table. Notice how parameters a and b have real-world meaning, namely they're the smallest and largest values. We will often look at how to use parameters with a distribution family in a way that has real-world interpretability. Now let's look at one more math representation of a discrete uniform. In this case, it is a plot of little f of x, the probability mass function, versus x. Here we read the plot like the table. All values of the support, in this the 3 values, 0, 1, and 2, get a probability mass point at 1/3. This is just a graphical view of a probability table, with the probability of the outcomes summing to 1, or 100%. But what happens if you want to model a scenario where any of the infinite real numbers between 0 and 2 occur with equal probability? In this case, we use big Z to represent this uncertainty and use a different distribution family. We use the continuous uniform, aka just the uniform distribution, to show this. This is also a 2-parameter distribution where the first parameter A is the minimum value and the second parameter B is the maximum value. But now any value between them, even something crazy like 1.64237, is potentially an outcome. With potentially infinite outcomes, the probability of any one outcome cannot really be positive. In fact, I want you to think of the probability of a single outcome being infinitesimally small, essentially 0. So instead of putting positive probability mass at certain points, here are 10 such points, we need a way to make probabilistic statements about all the infinite outcomes. In this case, our plausibility measure, still called little f of x, does not represent probability, but rather some indication of the relative likelihood of one value over another. The straight horizontal line here means little f of x is a constant value for all the infinite values between 0 and 2. This means all of these infinite values have equal plausibility of occurring. And since any one value occurring has essentially 0 probability, we have to talk about ranges of values of x to make any sort of probabilistic statement. Here, we know a number between 0 and 2 will occur with 100% certainty, and numbers outside of that range do not occur for this random variable. In this infinite possibility world, probability is represented by area underneath the probability density function. For example, the area of the shaded region is 1, or 100%. That means that the probability of a realization of x being between 0 and 2 is 100%. Now notice the area under f of x from 0 to 1 is 0.5, or 50%. The width of the rectangle is 1, and the height is 0.5. Doing width times height, 1 times 0.5, gives 0.5, or 50%. This means the probability of x being between 0 and 1 is 50%. We can also have distributions where the plausibility measure, aka probability density function, can take values greater than 1. That is because it is the area that represents probability. The area under this curve is exactly 1. Area underneath this curve is still 100%. The varied heights of the density implies values around 1, where the density function is higher, will occur with much greater frequency than x values, say, near 0 or near 2, where the density is smaller, and hence the area under the curve is much smaller. Big area here, small areas here. Let's get back to our continuous uniform 0-2 distribution where all the infinite values between 0 and 2 have non-zero plausibility. We use it to demonstrate one more math world representation, the representative sample. This is actually going to be our favorite representation, as the computational techniques we will use in this course often give us representative samples of probability distributions, not named probability distributions. Here is a representative sample from our named uniform 0-2 distribution. Notice all these 40 numbers are between 0 and 2. To be able to approximate the mathematical ideal of the perfectly horizontal density function line we see in the upper left, we will need a very large representative sample. Geom density in ggplot is the function that can get us a visual of this approximation. Here is the geom density plot using a 4 realization sample. Notice the plot looks nothing like the mathematical ideal, but as we increase our sample size from 40 points to here we have 4,000 points in the lower right, our density estimate looks closer to the ideal. It will be hard for us to know when we have a large enough sample to be considered representative, and by representative I mean when the properties of the sample and the mathematical ideal, those properties do not differ in any meaningful way, at least a way that impacts our decision quality. We want good decisions, but do not need mathematical precision to the 16th decimal point. As a rule of thumb, 4,000 points will be our starting point for a representative sample, and we will learn to find clues about when this number can be decreased without loss of representativeness, or increased to capture more of the properties, nuances, or sort of rare occurrences of some uncertain outcome. Okay, now, one last example of representing uncertainty in the math world. Here's a spinner pretended to be a real-world spinner. The arrow spins and will point to a number somewhere between 0 and 2. In this case, we get 0.421238.5. If this were a type of real-world uncertainty you were facing, some real-world stakeholders you work with are not going to like it if you get too mathematical when speaking with them. Many are just not trained to speak that way and will not appreciate you speaking a language they simply do not know. They weren't trained. So when speaking with these important domain experts and decision makers, we will use my favorite representation of a random variable, the oval. Don't laugh at my oval. I love my oval. Anytime you see this oval, it is secret code for a random variable. Stakeholders will intuitively understand that from the name you give the oval. In this case, we can call it spinner outcome. Behind the scenes, we will also have our math world representation as shown here. The oval will work wonders for both our collaborators and ourselves in fostering understanding as the scenarios we model get more complex. With math world representation in hand, there are 4 computer functions in R that we'll take advantage of to aid our understanding of named probability distributions. I will call the 4 functions dfoo, pfoo, qfoo, and rfoo. Foo is not the actual function name, and there's actually more than 4 of these functions. But computer scientists will use the word foo as a placeholder for something more sensical. In this case, the foo gets replaced by some abbreviation of a probability distribution. For the continuous uniform distribution, that abbreviation is UNIF, U-N-I-F, and thus the functions we will learn are dunif, punif, qunif, and runif. If you were investigating the normal distribution, then the functions would be dnorm, pnorm, qnorm, and rnorm. But let's learn the 4 functions using the continuous uniform distribution as our foo plug-in distribution. Dunif returns the height of the density function for any given value of x. So at x equals 0.2, the height of the density function is 0.5. For continuous distributions, that is ones with an uncountable number of values, this number is not that interesting because it is not a probabilistic statement. But the graphs of these density values can tell you about ranges of values that might be more plausible than others. In this example, all numbers between 0 and 2 are equally plausible. Punif returns the probability that a value is less than the given quantile, or cut point, of the distribution. This returns a probability. So here we see the probability that our spinner takes a value less than 1. This is also the area underneath the density curve for all values of x less than 1. See, this area is 0.5, and the function returns 0.5. Notice we could also give a vector of quantiles and get the element-wise probability associated with each of them. Qunif goes the other way. Give this function a probability and it returns the cut point such that the probability of a realization being less than that cut point equals the given probability. Here, we ask for the quantile such that 25% of the realizations will be below it. The function returns 0.5, and we see that the area under the curve below x equals 0.5 is 25%. Runif just gives you n realizations of the random variable. Here I ask for 1 random sample. Then I ask for n equals 3 random samples. Recall that we can execute the setSeed function immediately prior to each call for random numbers to ensure that the random numbers you see and the random numbers I see are the same. So in summary, we have lots of ways to represent our uncertainty in the math and computer worlds. Each one of them will prove valuable to us in different contexts, but inherently they are all just different perspectives of the real-world uncertainty we are modeling. As we dig deeper, each representation and the connections among them will become more ingrained in your brain. Work towards that kind of fluency by embracing them all and bringing them all into your life.